All right. Welcome to the second seminar of, there it goes again. Welcome to the second seminar of the spring semester. I'm very happy to introduce John Iacono, who in some sense doesn't need an introduction because he has been at Poly and NYU for many years until he escaped to a different place. So he's coming to us now from the Free University of Brussels, ULB, and I think I'm going to let him speak. Go ahead.
Thank you. Well, I think I got it. Okay, thank you very much. It's always happy to be back here and nice to see so many familiar faces here and online. So this talk is about incremental to the nearest neighbor. So the problem is geometric, which I guess makes it appropriate. And it's if you're given a bunch of points and these black things are supposed to represent points and not little smears, and you're given a query point, I want to know which black point is closest. So in this case, it's that one. So I hope you understand the problem. So what's the previous work on this? We care about dynamic versions of this. In other words, where you can insert and delete points. So points can come in, points can come out, and you want to support queries. I'm going to talk about this method of Bentley-Sachs in 1980, where you can do insert and log squared, query log squared. No deletion. Then Agarwal and Matushak in 95 came up with 2 points on the trade-off. They said you can get your query being log if you're willing to have your insert be a root, or you can have your query be a root if you're willing to have if you want the insert to be a log. But we don't like things being roots. That's not very nice. As I tell students in algorithms, roots worse than logs. So then there is this series of paper by Chan, Not Chan, and Chan.
Yeah, what is query? I don't know.
A query is, given a point, what is the closest point?
Oh, no. Yeah.
Show me the nearest neighbor to a query point. So insert points, delete points, given a query, who's closest? That's it.
Okay.
So there's this whole series of papers by Chan, Not Chan, and Chan, which have a query of log squared. And then before log squared, you either had not supported deletions or whatever. And they have insertion and deletion times that keep getting better, like log 6, log 6, log 5, log 4. Okay. But all of these queries are fundamentally log squared. So our goal was to find something with a query time of log, single log, insert time polylog. We can actually get it down to log 1 plus epsilon, but that's not so relevant. But we don't support delete. So that's our trade-off. So we're the first ones to get a query time that's a pure, simple log without supporting insertions in, let's call it polylog. All of my explanation today will be polylog, but we don't support delete. Okay. So that's the history, and that's what we're going for. So you can see previously, the best known thing with single log for query had insertion time of n to the epsilon. So getting from n to the epsilon down to log is good.
And there is no lower bound that says you can get log everywhere.
No reason why you can't get log everywhere. So here we basically throw every technique we know at the problem. So this paper is complicated, and I'm going to try and give some insight as to the main geometric nuggets that are new and give an overview of the old pieces. So the old pieces include standard point location, static to dynamic transformation using Bentley-Sachs, fractional cascading, decompositions of planar graphs, including sampling. And so I'm going to try and show these various pieces, but the cute thing about this whole thing is it depends on one stupid geometric fact, which is very stupid, but is hard to believe. I'll get there. So, first off, if you spend any time around these sorts of problems, if you want to, there's these things called Voronoi diagrams, that this is a geometry seminar. You know what Voronoi diagrams are. It's the locus of points that's the closest to each of them. So given a query point, asking who's the closest point is the same thing as saying which cell of the Voronoi diagram you're in. So the classic standard solution to this, if I don't care about insertion and deletion, is compute the Voronoi diagram and create a planar point location algorithm for the point Voronoi diagram. So point location. Anybody know what point location means in this context? It's a place where you rent things. It's a point, and in French, location means rental. So this is a umbrella rental stand on the beach. So point location. Point location, the most elegant solution is due to Kirkpatrick in '83, which shows linear construction login query. This built upon things like planar separator theorem, which was the original solution to this by Lipton-Tarjan earlier. Anyway, so that's all known and old. The second thing to note is this problem is what's called a decomposable problem. A decomposable problem is if I split the data into multiple parts, I can get the answer from each of the parts and easily combine them. This clearly is true. If instead of points, if I have orange points and black points, if I know the closest black point and I know the closest orange point, I can very quickly find the globally closest point. Not all problems have this, but this does. So Bentley-Sachs in 1980 had a very general static to dynamic construction for any problem that's decomposable. And the method is simple enough. All you do is you have exponentially increasing sets of your stuff, in this case, points. And all you do is if you want to query, there's going to be a logarithmic number of these sets. You query in each set, and from those queries, you combine them. Now, how do you insert? If you insert something into the smallest set. Every time the size of something doubles, you copy everything into the next bucket, and you just rinse and repeat. And so over the lifetime of something, the points will keep going into bigger and bigger buckets. So essentially, over the lifetime of something, it's involved in log-n rebuilds. So if you looked at the Kirkpatrick method, since it's linear time to rebuild, that's constant for each. So therefore, this would give you a constant insert. Unfortunately,
May I interrupt for
Yeah.
a second? Are your bounds worst case or amortized?
our bounds are amortized.
Okay.
Very much amortized. Everything is amortized in these things. Yeah, good question. So here, the Bentley-Sachs method, you simply do point location in each of them and combine them. There's log n sets. Each of them you do point location in each of the sets. That gets you your log squared. Super easy. And insertion is log n. Okay? So this very easy way to get your log squared. Now, getting the log squared down to log while supporting insertion, what you'd like to do is to somehow use this framework, but instead of doing the search in each of these separately, once you do a search in one set, for that to somehow help you to search in the next set. This is a known technique, at least in 1D. So what's the 1D problem? The 1D problem is, suppose I give you a bunch of sets of points on lines, and I give a query horizontal line, and I want to know what is the point nearest to the query line, okay, in each of those sets. Now, of course, you can do binary search on each of those sets. Each of those sets have n points, and you have k sets. This is k log n, but can you do better? Well, yes. I'm sorry, I just rotated it 90 degrees for no apparent reason. So there's a technique called fractional cascading, which allows you to once you find the closest in one of these sets using binary search, you can find the closest point in the next set in constant time. And this technique was invented a while ago. This is Chazelle, I believe. I should have the citation here. Everything's by Chazelle, but it basically involves you add a lot of pointers. So hard to see. Well, let me do the previous one because that's easier. All you do is in each of these sets, I take every other item and I insert it into the set below. And then I take every other item, insert it in the set below, every other item, insert it in the set below. Okay, this almost works. Okay, except for like if I'm here and I need to jump there, it's far. So then you add pointers. Some of these points are real points, some of these points are samples. From each point, from each real point, you add a pointer to this nearest sample to the left and right. For each sample, you add something to the nearest real to the left and right. And you get this mess of pointers, but in fact, it works. It gives you enough information that you can always crawl. And because wherever you are, you're always close to a sample that came from the next one. So it allows you to walk these pointers. The details aren't so important, but the thing is in 1D, this is a known trick of how you don't have to search separately in each set. You can sample from a set, and using the sample, it helps you very quickly move from one set to the other. Yeah.
Why you said this is log? Why is log n?
Well, you need to do binary search in the first set.
Okay, but it should be k times log n.
K times log n if I binary search in each set. Instead, it's going to be log n plus k.
I like plus k. If you have to one point, you have a lot of neighbors. Then you need to do log search there among the neighbors.
Here we do binary search in the first set.
Yeah.
So that's log n.
Yeah.
And then in constant time, I find the neighbor in the next set.
Why it's constant time?
In constant time, in
Wait,
constant time.
why it's constant time?
Because the way the samples are done, you can always, wherever you are here, I ask who's the nearest sample on my level, and it's that guy. And when I move up, I know because every other one got sampled, I'm within a constant, I either go left or right 1 unit and I find the thing I'm interested in. It's a somewhat complicated web of pointers, but it works. Because remember, I'm sampling every other thing. So if I go here and ask who's the nearest sample to me, it's this one. And this,
Okay, let's go from the top.
no, you go from the bottom. You have to
Yeah,
go
but
from the bottom.
sample is better.
It's crucial that you go from the bottom. Because the samples are going this way in order for you to help search that way.
Okay, I think I don't believe you, but
Yeah. So you say, given this fractional cascading technique, which is well known in 1D, does this work in 2D? In other words, could I find in each of these separate sets the nearest neighbor and do this in log n plus k? And here k is log n, so log n plus log n would be lovely. And unfortunately, Chazelle says no. He proved a lower bound in 2004 that says, if you want to find the nearest neighbor in log n sets of points, you want to do this in log n time, you need at least quadratic space. So this, he says, no, you can't do this. Not possible. So we need to get around this.
Okay, I'm sorry, is it okay to ask, is there an easy way to give some brief intuition how you get such a lower bound?
No, not for me. No.
In which model?
I forget.
Is it the probe something?
I will refer you to the paper of Chazelle for the details of this. So we cannot, so the whole Bentley-Sachs method is find the closest in each, combine the answers. We can't do this. So Instead, we cheat. So given a query point, what we do is for in each set, we either find the closest point or we produce a certificate that whoever is closest to me, to the query point there, is not the globally closest point. In other words, I don't care about it because I don't actually need the closest point in each of these sets. I just want the closest point. So I either produce the closest point in the set, or basically I'm going to say there's nobody in this set that's closer than something I've seen already. The other sets. This circumvents the lower bound. And it turns out we can use this to solve the problem. So, yeah. So Chazelle says we cannot find the closest point in each set. So what we're going to do in each set is either we find the closest point, or I will deliver a proof, a certificate, that there is no point in that set that could be the globally closest point. In other words, every set in their thing is further away than the closest thing I've seen so far, so I don't have to bother to find the closest point. It's not worth it because it's not going to be the answer. Okay? So with this trick, the lower bound doesn't apply because we're not finding the closest point in every set. So to be precise, and again, this is delving into details a little bit, what we're going to do is come up with a method that given some set and some k, that we're going to, looking at the sets from 2 to the k to 2 times 2 to the k, so whatever, if that's 16, so we're going to look from 16 sets away to 32 sets away, that we're going to produce a certificate that either we find the closest point in these sets, or we're going to say no point in these sets is closer than the closest in SI. So in other words, I found the closest here already. Can I ignore all of these? And we're going to produce the certificate in time k. Sorry, this should be in time. This should be in time 2 to the k. In other words, constant per set.
I'm a bit more confused about why do we need a certificate and we don't believe them to just tell us it's irrelevant?
Well, by certificate, you have to. Certificate is a bit exaggerating. The algorithm just ignores things that are irrelevant,
Okay.
but it does this by determining so.
I understand. Okay.
Yeah. Certificate's just a fancy word here. So let me get to this incredible geometric fact, just stunning. So suppose you have two sets of points, call them SI and SJ. And suppose that you take some points from SJ and you add them to SI. Again, we're doing this sampling method. The idea is you add some samples and somehow this helps you. I'm not going to say anything about samples. So about how we sample will be later. So there are some things that, so SI and SJ are no longer disjoint. There are some things in SI and SJ. Now, what I want to know is if we know our nearest neighbor in SI, could this possibly help us to find the global nearest neighbor? So I found the nearest neighbor among the blues. Does this help me to find the nearest neighbor among the oranges? So I've since discovered this is not due to Euclid, but when I wrote the slides, I didn't know who it was due to, so I said Euclid. So here's the stupid geometric fact. So look at Q. I'll say it, and then I'll let you stare. But here's the fact. If Q's closest orange is also a blue, then Q's closest point is a blue. The first time we sent this paper somewhere, it got rejected because they didn't believe this.
I'm lost a bit about what's happening here.
It's pretty,
Obvious, obviously.
it's too obvious. Okay. So let's try and prove this. Okay. So
So you have orange points, and you have blue points, and you have
Orange and
points
blue.
which are
orange and blue.
Are those arbitrary?
These are any points. Some are orange, some are blue, and they're not disjoint.
So you mean that if your closest point is blue, then it is blue.
Yes.
Oh, I see.
Look. No, that's not what it's saying, because here, for example, Q's closest point is this one.
I know,
Yeah,
but it's blue.
yeah, I agree. So
If it's not orange, it is blue. So that's what you're saying.
look at, so suppose Q's closest point is a blue that's not orange. Then the theorem is satisfied, right? Suppose it's a blue and an orange, then it's satisfied.
That's an orange, yeah.
But could Q's globally closest point be an orange that's not a blue? No, because what's the if? If its closest orange is also a blue.
So it's not a geometric statement, it's basic logic in some sense.
It's basic logic in some sense. Yeah, that's why I realized it's not Euclid, because it's just it's so okay. Do you believe this?
Yes.
Okay. So now most of the paper now follows, let's take this simple fact to the extreme. Here's a pretty picture. I once again have orange points, blue points, and they're not necessarily disjoint. I've also incredibly accurately done the Voronoi diagram of the blue points, of which there's 5 points, and the Voronoi diagram of the orange points, of which there's a bunch. So look at the query point Q. How do you find Q's closest orange point? Well, which cell am I in? I'm in that cell. Is this also a blue point? Yes.
You're not
Therefore,
in that cell.
what?
You're not in that cell.
No, I'm in this cell.
Oh, the orange cell.
Orange cell. Again, I'm asking who is your closest orange point?
Uh-huh.
My closest orange point is this. It happens to be a blue. Therefore, I know my globally closest is blue. Which blue? This one. Why? Because I'm in that cell. Okay. Again, logic. Q's closest blue is P because you're in the blue cell of P. Q's closest orange is R because you're in the orange cell of R. It's also a blue point. Therefore, Q's closest globally must be blue, which means its closest is P because my closest blue is P. Yes? Now, what is the locus of points for which this statement holds? Clearly, it holds for anybody in this cell, yes? Let me color it. It also holds anybody in those cells. The same reason. In other words, what I'm coloring is those points whose orange cell is a blue and are in the blue cell of P. Notice always in these pictures, these cells are coming in from the edge because the point that their center point is outside of the cell. Could this R be inside this cell? No. Why? Because these is the points that are closer to P. Okay, so this necessitates the fact that this must be outside. Making sense so far?
Yes. I cannot say where this is going, but yes.
It's hilarious. It's all very basic, yes? Okay, so we've established that globally, the closest points of all these purple things are P. What is the locus of points that are globally their closest point is P? It's a Voronoi region of all the points. What do we know about Voronoi regions? They're convex. So not only that and that, but all of these have this property. So if you find yourself in this region, you can ignore the orange points. All right? Because you know this blue point is closer than any orange.
Okay. Sure.
Yeah, and this is our point, is trying to determine how, given two sets, using geometry, you can ignore the other set. If I find ourselves here, I know that our closest point among the orange and the blue is this blue point P, and I do not have to go through the effort to find who my closest orange is. Okay.
So you check random orange points, and then you take convex column. That shape, right? Or what would you
We're getting to have the details of the sampling. So this for now works for any blues and orange points.
This would work even if there's some orange non-blue point that's inside of the blue cell there.
Yes. Yes. This again was why we got rejected the first time, because they said, no, what if you had an orange in there? But no. Even if the orange was inside, it's okay. This logic still holds. Yes. It's all from first principles. Okay. So if you can compute this region and store it.
I'm sorry, I don't get it. But what if you have an orange point just next to P?
Okay. What if you have an orange point just next to P?
Then the nearest neighbor of the purple region stays the same.
Yes.
So and so that means that the blue Voronoi diagram stays the same.
Yes.
However, if now I
No, but the orange Voronoi diagram changes. If the orange puts you on top of P, then this region will disappear. Because remember, this is defined by the Voronoi in orange.
Yeah.
So if I take an orange point and move it here, then the orange Voronoi boundary is exactly the same as the blue.
Yeah, okay, that's right.
Yeah.
Okay, makes sense.
This again, not
Yeah.
so intuitive, but you move the orange here. This point is orange Voronoi diagram. If the orange and the blue are the same, then the Voronoi diagrams are the same, and this orange cell wouldn't go inside the blue cell.
Okay, so in this picture, no orange can actually be inside that region.
It could be a little bit. If I move it here, this probably only moves it a little bit.
But not in the green region.
Oh yeah, not in the green. It's completely it's geometrically impossible. The green region will move. Okay, so we need to be able to compute this. Computing it isn't that hard, but really what we want to do is then we want to test whether or not a given query point is in this region or not and try and figure things out. this region could be quite complex, which means testing it could be bad. So we need a little more work. Now let's talk about sampling. I haven't talked about how we sample. So far, I just said, oh, there are some things that are orange and blue. Okay. The way we're going to sample is to use a result of Fredrickson from '87 about sampling. And he says that you can pick some constant and you can basically pick whatever size you want. And given a planar graph, a planar diagram like this, you can partition the cells into regions. So here I've colored the regions so that they're interior disjoint. Okay, so they can overlap on the edges. So essentially I want to group them into things that are interior disjoint. And the main point here,
What do you mean interior disjoint? So this is Voronoi diagram, right?
this is a Voronoi diagram, but this statement has to do with just planar graphs. So in other words, here you see green is all of these, and blue is all of these. And they overlap, like this cell is in green and blue.
Okay.
Okay. And so you can split them into pieces such that the exterior of each piece has the square root of the amount of stuff in the interior. Basically, I always like to think of things on grids. If I were given a grid graph, basically I can split the grid graph into cells such that the exterior of each cell is the square root of the interior, and they only overlap on the edges. But you can do this in general for any graph. This is, basically a result of planar separators.
Planar graphing.
Yeah, any planar graph. Yeah, it has to be a planar graph. Okay. And what we're going to use.
How hard is that? I mean, how many pages it will?
This, I think it follows fairly straightforwardly from planar separator theorem. And what we're going to do is our samples that we're going to choose from one set that we move to the other are these fringe points. These are the exteriors. Okay. Again, we're trying to make it so that given one set, I'm giving some information to another set to help point location. So what's nice intuitively is if I pass these samples down, I know that if you're in the middle of the samples, you're somewhere in here. And remember, in here, I'm going to have the square of the amount of stuff on the outside, which is great. Okay. So it's a low order amount of stuff. What is crucial about this, and what's very interesting, is that with this statement, for example, if I split these things, if I say this has, x squared things and the fringe has size x, can I say anything about the complexity of these Voronoi cells? The things on the fringe, I know nothing about their complexity, right? Because a Voronoi cell could be arbitrarily complex.
But they're together, you know the total number of pages, right?
I know the total number of edges, but that could be big. But so what's interesting here is that, again, if I have x things on the fringe and x squared things on the inside, I know that the complexity of the inside, that this boundary here is only complexity x, whereas the exterior boundary is unbounded. It could be n. Okay? Because the complexity of this is defined by the number of cells on the fringe. Okay? Does that make sense?
Yeah, but maybe the x times square root of x, so what x?
I'm just saying you're picking any x. In fact, I'm picking an x which is exponential in the difference between the two sets, but let me leave that for
So
now.
x is number of points inside, right?
Yeah, let me say x is the number of things on the fringe and x squared is the number of things inside.
Okay, then why it is x, so why the number of edges is x?
Well, you know here that the number of edges inside here is at most x squared total. And here, the problem is this is unbounded. This could be n. Because the things in here are only adjacent to other things in here or the exterior. Whereas the things here could be adjacent to an unbounded number of things.
I think what he's asking is why is that number not x squared?
It could be x squared.
Okay.
Yeah, it could be x squared.
Ah, it could be.
Yeah, it could be x squared, but it's bounded in terms of x. Whereas
okay.
the exterior ones are not bounded in terms of x.
Right.
Yeah. I mean, we're going to be doing searching, so all that matters is when you search, when you log it, you get a log x and not log of an unbounded number. So observations, no bound on the complexity of the Voronoi of a piece.
So this, they mean this is polynomial from x.
Yeah.
Okay.
Yes.
So the equal exponent of x then.
Yeah, as I said, if you're sitting there and my x again is j minus I can do point location in time order j minus I on the interior. Okay. Point location on the interior in order x, because it's x squared things, log of x squared is log x. That's it. Yeah. So I can't do point location on the fringe pieces because I don't know their complexity. But I can do point location on the interiors.
I mean, because we have a bounded number of total number of edges, it's x squared something, 6 of square.
Yeah.
So you just check all inequalities and it's
Yeah, I mean, you can just use this Kirkpatrick method and it's logarithmic. Here's another picture of, suppose I have 4 pieces. So this piece has this fringe, this white piece has this fringe, this white piece has this fringe. And this really goes to show that you could have a very unbounded piece on the fringe that's shared in many fringes, but yet each of these pieces, because these are only going to have complexity, polynomial in x, I can do point location in these guys, but I can't do point location there. So in other words, I can do point location on the interior of these partitions. Let me go back to the picture. So going back to the picture, remember I said our samples always pierce in from the outside. Okay. So now it makes sort of weird diagrams that these areas that I care about always come in from the outside and they could do weird shapes like this. But all of these shapes are these Voronoi regions from the orange set that happen to have a sample, and they all come in from the outside. But now notice, now these are the fringe, so somehow these are the exterior of connected pieces, and I know that these white regions have a nice complexity. So what we end up doing is the following. Well, first, so we said, I want to determine whether or not you're in the green polygon, which is the convex hull of all of the red stuff. And then what I do is from the center point, I split this thing into triangular pieces. And now what I want to argue is within each triangular piece, the complexity is bounded. In other words, this whole thing could be have high complexity, but within each piece, this is the very cool thing about it, that if I look at how the green line intersects one triangular piece, it could go across the boundary and then have two lines. That's it. It's just that because all of these pieces start on the boundary, there's nothing else that can really happen here. And the end result is these two regions are white regions, which means they're inside one of the cells of the cutting, and thus I can afford to do point location in them. So therefore, I can in constant time see whether or not I'm inside or outside. If it's inside, I say, okay, that's the answer. If I'm outside, I need to do point location on that sample, but the sample, I'm on the interior of the sample, and therefore it was of enough bounded complexity that I can afford to do the point location. Okay. This is a high-level overview. There are more details as I put UG there, but I'm trying to get an idea of the geometry that's happening here. Okay. So still lots of room for improvement. Let me talk about just at a high level some further results since this paper was published. So Yakov came and visited in the fall, and we worked all fall with Martin Seibold, who's a postdoc with me. And we were able to generalize this to the following. So consider the problem of given n planes in 3D. Suppose I want to insert the planes in polynomial time, and given the planes and a vertical ray emanating from negative infinity, I want to report the first k planes that it hits. Okay? And I want to do this in time log n plus k. Okay, so in other words, again, insertion, polylog, but I want the best possible runtime for a query. And again,
So you have linear equations and you plan to find the first k smallest value for an edge.
yeah, in 3D. So this is a special case of the previous problem, because it's known that if you want to compute a Voronoi diagram, one way to do this is you can take the points, see where they're tangent to a parabola, and then look at the
You mean it's a generalization?
yes, it's a generalization, sorry.
Weighted for Voronoi diagram.
No, just standard Voronoi diagram. You just project the points onto a parabola and look at the envelope.
You can also do weight for another.
You can also do weighted Voronoi diagrams. So this is general in two ways. One is that we can deal with any planes, not just planes that arise from this projection. And instead of just finding the first point, we can find the first k points. This, for example, allows us to do, you could do k-order Voronoi diagrams or more complicated things.
Yeah, so 7 points of rule, then it's like instead of points, you consider circles. And then you consider power of points.
Yeah, this is a power diagram.
Yeah.
So this also allows things like k nearest neighbor and plane. And if you look at the dual of this, it becomes 3D half space range reporting. So in other words, given points in the plane and a query plane, count how many are on one side in time log n plus k, which this is quite good for small k. This was not known. Why is this more complicated than what I talked about? Well, what I talked about was already fairly complicated, and in the end, getting it details are annoying. Well, you need to work with either order k Voronoi diagrams or in general k levels of arrangements of planes. If you remember the picture I put up before, I had this thing that I was doing logic from. Whereas if you're dealing, that's the site of the Voronoi diagram. If you're dealing with a face of a k level, there's no site. It's just a face. So some of the logic needs to be adapted to the fact that there's no actual site to deal with. Additionally, the needed certificates are more complicated because now I need the fact that I want to exclude a set if none of the points there are among the kth compared to what I've seen before. So before I said, okay, anyway, you see, it's much more annoying. And the other thing is, before, even once I identified sets that I could query, I could get the closest one here, closest one here, closest one here, and compare. But suppose this set has one of my answers, this set has one of my answers, this set has one of my answers. I can't afford for each of them to give me k answers and then for me to combine them, because that would take k squared time just to deliver the answers. So I need to somehow keep on exponentially asking things to be delivered. And we use a technique. I see Sarita is talking in a few weeks, and she had a paper that was very useful in figuring out this part of it. The good news is that this result really is only challenging when k is smaller than log squared, because when k is larger than log squared n, we can just use Bentley-Sachs as is, because Bentley-Sachs had a log squared query, and if k is log squared, then fine, just use that. This is very good because the complexity of the k level of the arrangement is nk. So n times log squared, that's still fine for our insertion time and stuff like that. Whereas if it went higher, that would be out of control. So this allows us to construct these things. So the main open problem here is how ours is insertion only, completely insertion only. Whereas the whole work of Chan, not Chan, and Chan involves using shallow cuttings, which are a type of cutting, and they put things into buckets, and once a bucket gets more than half empty due to deletion, they take everything from the bucket and reinsert it in the beginning again to make sure everything still works out. This naturally leads to polylogs. And we've spent a lot of time trying to figure out, is there a way that we can combine Chan's shallow cutting with what we're doing to try and support deletion? And again, we are happy to have any sort of polylog, and we've gotten nowhere. We've spent weeks on this.
So your right now, your insertion is what?
Is polylog, we can actually do log to the 1 plus epsilon.
Okay, and your query is log.
Queries log.
So
The key thing is to have the query be just log. Yeah, because all of the shallow cutting stuff gives polylogs, and you can squeeze the polylogs and whatever, but log squared seems really inherent in the shallow cutting stuff.
there's nothing with log query insertion and deletion.
No, nothing with unless you're going to roots. Yeah. So this is clearly the next open thing to sort of nail down this whole path. Okay, that's all.
Thank you.
Very interesting.